Right now, somewhere between Mars and the Sun, a Manhattan-sized object from another star system is doing something that has never been documented before in human history. It's growing a tail. And according to one Harvard scientist, this tail might be evidence of controlled maneuvering. 3I Atlas, the third confirmed interstellar visitor to our solar system, has just entered a phase that could rewrite everything we thought we knew about these cosmic wanderers. Because here's what makes this different from any comet we've ever tracked. This thing already had what scientists call an anti-tail, a forward-facing plume that defied normal physics. Now, as it barrels toward its closest approach to the Sun on October 29th, it's developed a traditional tail streaming behind it. The anti-tail-to-tail transition. It sounds technical, mundane even. But if Harvard astrophysicist Avi Loeb is right, we might be watching the first documented evidence of an alien spacecraft completing a braking maneuver and beginning its acceleration phase. Let's be clear about what we're dealing with here. This isn't speculation built on grainy photos or misinterpreted data. We have multiple observatories tracking this object in real time. The Nordic Optical Telescope in the Canary Islands captured the transition in September. The Gemini South Telescope in Chile has provided the clearest images we've ever had of an interstellar object. NASA's HiRISE camera on the Mars orbiter grabbed shots when 3I Atlas passed within 12 million miles of the red planet earlier this month. Those Mars images, by the way, would be the highest resolution photos of an interstellar object in human history. NASA hasn't released them yet. Government shutdown. So we're sitting here, waiting for images that could fundamentally change our understanding of what's visiting our solar system, and they're locked behind bureaucratic delays. But even without those photos, what we're seeing is unprecedented, and it's happening fast. In just 4 days, on October 29th, 3I Atlas will reach perihelion, its closest point to the Sun, coming within 130 million miles of our star. That's 1.4 astronomical units, almost 1.5 times the distance between Earth and the Sun. For context, most comets go wild when they get that close. The ice sublimits, jets of gas and dust explode from the surface. Tails grow millions of miles long. It's a spectacle. And 3I Atlas is putting on that show right now. But it's the sequence of events that has scientists intrigued and, frankly, a little unsettled. First came the anti-tail. Not a tail streaming behind the object as solar radiation pushes material away from the Sun. An anti-tail. A plume shooting forward in the direction of travel. Analysis of that plume revealed something that set off alarms across the astronomical community. It contained materials that included a nickel alloy never seen in nature. An alloy only known from human manufacturing. Water, carbon dioxide, cyanide, those you'd expect from a comet. But a manufactured nickel alloy? That's not natural. That's engineered. Now, before we spiral into science fiction, let's acknowledge the conventional explanation. Maybe, under extreme and unknown conditions in some distant star system billions of years ago, natural processes created this alloy. Maybe there are formation mechanisms we don't understand. Maybe. But here's where it gets interesting. That anti-tail, which Loeb described as potentially indicative of a braking thrust, has now transitioned into a traditional tail. The images from the Nordic Optical Telescope show material being stripped off the rear of the object as it accelerates toward the Sun, getting hammered by up to 33 gigawatts of solar radiation. If you're piloting a spacecraft from another star and you need to slow down as you enter a solar system, you'd fire your engines forward, creating thrust that opposes your direction of travel. That would produce a forward-facing plume, an anti-tail. Then, once you've shed enough velocity, you'd reorient, possibly to adjust course or accelerate toward your target. That would produce a tail streaming behind you. That's the sequence we just observed. Now, is 3I Atlas an alien spacecraft performing a controlled maneuver through our solar system? Or is it an ancient comet, 7 to 10 billion years old, reacting to solar radiation in ways we're still trying to understand? The answer matters, because if it's the former, we're living through one of the most significant moments in human history, and most people have no idea it's happening. This is where the International Asteroid Warning Network enters the picture. Earlier this week, they added 3I Atlas to their official target list. Not because it poses a collision threat, it doesn't, but because this object represents an unprecedented scientific opportunity. They wrote on their website, "While it poses no threat, Comet 3I Atlas presents a great opportunity for the IAWN community to perform an observing exercise due to its prolonged observability from Earth and its high interest to the scientific community." Prolonged observability. That's key. Unlike Oumuamua, which zipped through the inner solar system in 2017 before we could barely get our instruments pointed at it, 3I Atlas has been visible for months. We've had time. Time to study, time to analyze, time to watch it evolve. And what we've watched is something behaving in ways that keep defying expectations. Let's talk about what should be happening versus what is happening. At 1.4 AU from the Sun, a typical comet would be active, sure, but not violently so. Water ice doesn't sublimate aggressively at that distance. You need to get closer, inside about 1 AU, before water really starts outgassing in large quantities. But 3I Atlas has been spewing water for months. 40 kilograms per second, like a fire hose on full blast. At distances where that shouldn't be possible. The composition offers a clue. This comet is extraordinarily rich in carbon dioxide, with an 8-to-1 ratio of CO2 to water. Carbon dioxide sublimates at much greater distances from the Sun than water ice. So the CO2 has been outgassing for a while, and it's that outgassing that's driving the activity. But here's the thing. As 3I Atlas gets closer to the Sun and temperatures rise, the water is going to start sublimating more aggressively. The tail we're seeing now, it's about to grow, dramatically. When this thing emerges from behind the Sun in early November and becomes visible again, it could look completely different. Bigger, brighter, more active. Scientists are preparing for that moment. Telescopes on the ground, in orbit, even instruments on spacecraft en route to Jupiter are being redirected to capture what happens next. Because whatever 3I Atlas is, comet or craft, it's about to give us the show of a lifetime. And we have a front row seat. The question is, what will we see when it reappears? Let's rewind for a second. How did we even spot this thing in the first place? July 1st, 2025. The Atlas Survey Telescope in Chile, an automated system designed to scan the sky for asteroids and comets, flagged a faint object moving against the background stars. In isolation, not unusual. Atlas finds objects all the time. But as data accumulated over the following days and weeks, astronomers realized something was off. The trajectory wasn't elliptical. It was hyperbolic. That's the signature of an interstellar object. Something not bound by the Sun's gravity. Something passing through. Confirmation came quickly. Within weeks, observatories around the world had locked onto 3I Atlas and verified its interstellar origin. It was traveling at 210,000 kilometers per hour relative to the Sun. Fast, but not absurdly so for an object in interstellar space. Its trajectory could be traced back through the galaxy, and when astronomers ran the numbers, the results were staggering. This object is ancient. 7 to 10 billion years old. It formed billions of years before our Sun even existed, in a star system that might not even exist anymore. Think about that for a second. You're looking at an object that witnessed the early universe. It formed when galaxies were still young, when star formation rates were at their peak, when the cosmos was a very different place, and it's been wandering the galaxy ever since, surviving radiation, cold, cosmic rays, collisions with interstellar dust. And now, by sheer chance, it's here, passing through our neighborhood, giving us a glimpse of a world we'll never visit. Except, it's not behaving like a passive chunk of ice drifting through space. It's active. It's shedding material. It's changing. The Gemini South Telescope image from August 27th is stunning. You see 3I Atlas streaking through the frame, a faint coma surrounding the nucleus, the tail just beginning to form. The stars in the background are smeared into lines because the exposure tracked the comet's movement. It's a snapshot of motion, of something journeying. But zoom in on that coma, the glowing cloud of gas and dust surrounding the nucleus, and you see structure. Jets, plumes, material being ejected in specific directions, not uniformly. That's not random. That suggests active regions on the surface, areas where sublimation is concentrated. On a natural comet, those active regions are usually associated with surface composition variations. Maybe one area has more ice, another more dust. As the sun heats the surface, the ice-rich regions outgas more aggressively, creating jets. But on a spacecraft, active regions could be thrusters, vents, controlled releases of propellant. This is the ambiguity we're stuck in. Every observation that could support the "it's just a comet" hypothesis can also be interpreted through the "it's something else" lens. Avi Loeb has been vocal about this. In his recent paper, he laid out the case for why the anti-tail-to-tail transition could indicate controlled maneuvering. He's not saying it is a spacecraft. He's saying we can't rule it out. And given the stakes, we should be taking that possibility seriously. Because if there's even a 1% chance that 3I Atlas is artificial, then observing it becomes the most important scientific endeavor of our time. But let's ground ourselves in what we know for certain. We know the object is roughly 2 to 6 kilometers across. Estimates vary because we can't resolve the nucleus directly. It's too far, too small, surrounded by a coma that obscures the surface. But based on brightness and activity levels, 2 to 6 kilometers is the range. For comparison, that's about the size of Manhattan, or Mount Everest. It's massive. 33 billion tons of material, moving at interstellar speeds. We know its composition is dominated by carbon dioxide, with water, cyanide, and trace amounts of other volatiles. The nickel alloy is the wild card. No one expected that. No one has a fully satisfying explanation for it. But it's there, documented in spectroscopic data. We know it's old. The trajectory backtracking and isotopic analysis, if we had samples, which we don't, suggest formation in the early universe. This is a relic, a fossil from a time when our galaxy looked completely different. We know it's been active since at least early August, when the first outgassing was detected. That's unusual. Most comets don't turn on until they're much closer to the sun. But 3I Atlas was already spewing material at 3 AU, 3 times the Earth-Sun distance. And we know it's about to get more active. A lot more. When 3I Atlas swings around the sun on October 29th, it will be subjected to intense heat and radiation. The surface temperature will spike. Sublimation rates will increase. The tail will grow. And depending on how much volatile material is left on the surface, we could see dramatic outbursts. NASA's SOHO spacecraft, which monitors the sun, might catch glimpses of 3I Atlas as it makes its closest approach. The images would be low resolution, but they'd give us a sense of the comet's behavior in the most extreme environment it will encounter during this pass. Then, in early November, 3I Atlas will reappear in the pre-dawn sky, having survived its solar encounter. Telescopes will be watching, cameras will be rolling, and we'll see what it looks like on the other side. Will the tail be longer? Will the brightness have increased? Will there be signs of fragmentation, chunks breaking off due to thermal stress? Or will it look more or less the same, suggesting a resilient structure capable of withstanding extreme conditions? That resilience, by the way, is another point in favor of the something unusual hypothesis. Natural comets, especially ancient ones, tend to be fragile. They break apart. They shed layers. they disintegrate. 3I Atlas has been traveling through interstellar space for billions of years, getting bombarded by cosmic rays and high-energy particles. The surface should be heavily damaged, eroded, and yet it's still intact, still active, still shedding material in a controlled manner. How? One possibility: it's been dormant for most of its journey, frozen solid in the deep cold of interstellar space, where temperatures hover just above absolute zero. In that state, chemical processes essentially stop. There's no weathering, no erosion. The comet becomes a time capsule, preserved for eons. Only when it enters a solar system and begins warming up does it become active again. The ice starts sublimating, jets form, tails grow. It wakes up. If that's the case, then 3I Atlas might have passed through dozens, hundreds, maybe even thousands of star systems over its lifetime, activating briefly each time before returning to dormancy as it drifts back into interstellar space. A wanderer, a cosmic nomad, traveling the galaxy, visiting stars, moving on. There's something poetic about that, and also slightly eerie. Because if that's true, then interstellar space is filled with these ancient, dormant objects just waiting for the next star to wake them up. And occasionally, one of them finds its way here. Now, here's where things get genuinely strange. And I mean strange in a way that makes scientists uncomfortable. The transition from anti-tail to tail isn't just visually dramatic. It represents a fundamental change in how material is being ejected from the object, and the timing is suspicious. When 3I Atlas first developed its anti-tail back in August, the plume was pointing forward, in the direction of travel. Material was being expelled ahead of the object. For a natural comet, this can happen under specific circumstances. If the comet is rotating in a particular way, or if solar radiation pressure is interacting with the coma in unusual ways, you can get forward-directed jets. But those explanations require very specific conditions, and they don't account for the composition of the plume, that nickel alloy, the one that's never been seen in nature. Loeb's hypothesis is straightforward. If you're trying to slow down a massive object traveling at interstellar speeds, you need thrust opposing your direction of motion. Fire your engines forward, and you create a plume of exhaust ahead of you. That's the anti-tail. Once you've shed enough velocity, you either shut down the engines or reorient the craft. At that point, natural outgassing takes over, or you switch to a different propulsion mode. Solar radiation starts stripping material off the rear of the object. That's when you get the traditional tail. The sequence matches, almost perfectly. But here's the counter-argument, and it's a strong one. Space is weird. Comets do unexpected things. We've seen comets fragment for no apparent reason. We've seen them brighten suddenly, dim unexpectedly, develop multiple tails, split into pieces, and defy predictions. 3I Atlas could just be another example of how little we truly understand about cometary behavior, especially for objects from other star systems where formation conditions might be radically different from anything in our solar system. Except we've now studied 3 interstellar visitors, and all 3 have been bizarre in completely different ways. Oumuamua accelerated as it left the solar system. No visible outgassing, no tail, no coma, just acceleration. Scientists eventually settled on the explanation that it was outgassing something we couldn't detect. Maybe hydrogen, which is invisible to most telescopes. But that explanation required some creative physics. The acceleration was real. The cause remains debated. Borisov, the second visitor, was the normal one. It looked like a comet, acted like a comet, had a composition similar to comets from our own Oort cloud. High carbon monoxide content, sure, but within the range of what we'd expect. Borisov was reassuring. It suggested that interstellar comets weren't all going to be weirdos. And then came 3I Atlas. ancient, carbon dioxide rich, spewing water where it shouldn't, sporting a manufactured nickel alloy, and now transitioning from an anti-tail to a tail in a sequence that looks suspiciously like a spacecraft maneuver. 3 visitors, 3 wildly different profiles, and the statistical implication is staggering. If we've detected 3 interstellar objects in just 8 years, and all 3 are this diverse, then our galaxy must be absolutely teeming with these things. Thousands, maybe millions, passing through the solar system every year, most of them too faint or too fast for us to detect. We're only seeing the tip of the iceberg. And here's the unsettling part. We have no idea what most of them are. We catch the bright ones, the active ones, the ones that happen to pass close enough to Earth that our telescopes can spot them. But the dark ones, the inactive ones, the ones moving at different angles or speeds, they're invisible to us. Which raises an obvious question. How many artificial objects could be slipping through our solar system completely undetected? If a civilization wanted to send probes to neighboring star systems, the logical design would be something that blends in. Something that looks like a natural object. A comet, an asteroid, maybe even a cloud of dust. You wouldn't send a shiny metallic spacecraft broadcasting radio signals. You'd send something quiet, something camouflaged. And if you wanted it to be autonomous, capable of navigating between stars without constant communication, you'd give it decision-making ability. The ability to adjust course, to slow down, to investigate points of interest. Like planets. Or, more specifically, planets with atmospheres. Planets with water. Planets with biosignatures. Planets like Earth. Now, before anyone accuses me of going full conspiracy theory, let me be clear. There is currently no evidence that 3i Atlas is targeting Earth or has any interest in our planet. Its trajectory takes it nowhere near us. After perihelion, it will head back out into interstellar space, and we'll never see it again. But the fact that we're even having this conversation, the fact that serious scientists are publishing papers discussing the possibility of artificial interstellar objects tells you how much the paradigm has shifted. 10 years ago, suggesting that an asteroid or comet might be an alien probe would have been career suicide. You'd be laughed out of the room. But Oumuamua changed that. The weirdness of that object, the inability to fully explain its behavior with conventional models, opened a door. And now, with 3i Atlas, that door is opening wider. The International Asteroid Warning Network's involvement is significant. This is a group coordinated by NASA and other space agencies specifically to track near-Earth objects that could pose impact threats. They monitor asteroids, calculate orbits, run simulations, and prepare response plans. For them to add 3i Atlas to their target list, not because it's dangerous, but because it's scientifically important, signals that the scientific community recognizes this object as something extraordinary. Their statement is carefully worded. While it poses no threat, Comet 3i Atlas presents a great opportunity for the IAWN community to perform an observing exercise. An observing exercise. That's the official language. But read between the lines. They're mobilizing international resources to track this thing. They're coordinating observations across multiple observatories. They're treating it like a high-priority target. Why? Because opportunities like this are rare. We might not see another interstellar visitor this well-positioned for observation for decades. And if there's any chance at all, that this object is more than just a comet, then every data point matters. So what happens next? In 4 days, 3i Atlas reaches perihelion. It will be closer to the Sun than it's been at any point in its multi-billion-year journey. The surface will heat up, volatiles will sublimate, the tail will grow. And we'll be watching. NASA's Solar and Heliospheric Observatory, SOHO, will likely capture images as the comet passes through its field of view. The resolution won't be great. SOHO is designed to study the Sun, not comets, but it'll give us a sense of how active 3i Atlas becomes under maximum solar heating. Ground-based telescopes will be tracking it right up until it disappears behind the sun. And then, for a few weeks, we'll lose sight of it entirely. It'll be on the far side of our star, hidden from view. That period, when we can't observe it, is going to be agonizing for scientists. Because anything could happen. The comet could fragment. It could have a massive outburst. It could change trajectory. And we won't know until it reappears. Early November. That's when 3i Atlas will become visible again, emerging from behind the sun in the pre-dawn sky. Telescopes will lock on immediately. Cameras will start recording. Spectrometers will analyze the light. And we'll see what it looks like after its solar encounter. If it's just a comet, we'd expect to see changes. Maybe the tail is longer, brighter. Maybe there's evidence of fragmentation, smaller pieces trailing behind the main nucleus. Maybe the activity level has increased, or decreased, depending on how much volatile material was lost during perihelion. But if it's something else, if there's any truth to the artificial object hypothesis, then what we see might be completely unexpected. Maybe the tail disappears. Maybe the object reorients. Maybe it changes velocity in a way that can't be explained by solar radiation or outgassing. We won't know until it happens. And that's the hook. That's what has the scientific community on edge. We're in a holding pattern, waiting for an object we don't fully understand to do something we can't predict. Meanwhile, those high-rise images from the Mars orbiter remain unreleased, locked away due to a government shutdown. The highest resolution images of an interstellar object ever captured by human technology, and we can't see them. The frustration in the scientific community is palpable. Researchers have been waiting for those images for weeks. They were supposed to provide clarity, details about the surface structure, the nucleus size, the activity patterns. Instead, they're sitting in a database somewhere, inaccessible. It's a reminder of how fragile our infrastructure for this kind of research really is. We have billion-dollar telescopes and spacecraft capable of incredible observations. But if the people managing the data can't release it due to bureaucratic issues, then all that technology is useless. Assuming the shutdown ends and the images are eventually released, what might they show? At 12 million miles, HiRISE would have been able to resolve features on 3i Atlas down to maybe a few dozen meters. Not enough to see fine details, but enough to get a sense of the object's shape, surface texture, and activity. If it's a typical comet nucleus, we'd expect to see an irregular shape, maybe elongated or lumpy, with active regions where jets are erupting. The surface would be dark, covered in a layer of dust and organic compounds that have been baked by cosmic rays over billions of years. But if the shape is too regular, too smooth, or if there are structures that look artificial, linear features, geometric patterns, things that don't fit natural formation processes, then we'd have a problem. A good problem in the sense that it would confirm we're dealing with something extraordinary, but also a terrifying problem, because it would mean we've been visited by technology from another civilization, and we have no idea what it's doing here or where it came from. Let's talk about the composition again, because it's crucial to understanding what 3i Atlas might be. The 8-to-1 ratio of carbon dioxide to water is extreme. In our solar system, comets typically have much higher water content. Water is the dominant volatile. CO2 is present, sure, but usually in smaller amounts. For 3i Atlas to be so CO2-rich suggests it formed in a very different environment, possibly a star system with a cooler star, where temperatures at the comet formation zone were low enough that CO2 ice could condense more readily than water ice. Or, and this is the alternative explanation, it formed in a molecular cloud, the dense interstellar regions where stars are born. In those environments, CO2 can be more abundant than water depending on the chemistry. If 3i Atlas is a rogue object, ejected from its birth star system billions of years ago and wandering the galaxy ever since, then it might carry the chemical signature of that ancient molecular cloud. Either way, the composition tells a story of a place very different from here, a place where the rules, the temperatures, the chemical processes were alien to us, and that manufactured nickel alloy sits in the middle of that story like a glitch in the Matrix. There are natural nickel-iron alloys. Meteorites contain them. But the specific composition detected in 3I Atlas's anti-tail doesn't match any known natural formation process. It's a blend that on Earth we produce intentionally for specific purposes. High-strength applications, aerospace materials, things like that. Could nature produce it under extreme, unknown conditions? Maybe. We can't rule it out. But the burden of proof is starting to shift. The more anomalies stack up, the harder it becomes to keep invoking unknown natural processes as an explanation. At some point, the simpler explanation becomes, it's artificial. Occam's razor cuts both ways. Yes, we should prefer natural explanations when possible. But when the natural explanation requires multiple layers of improbable coincidences and unknown physics, and the artificial explanation fits the data more cleanly, then which is really simpler? This is the debate happening right now in astronomy departments and research institutions around the world. And it's not a fringe debate anymore. It's mainstream. People are taking it seriously. Because here's the thing about science. It evolves. What seemed impossible yesterday becomes routine tomorrow. Continental drift was laughed at. Meteorites from space were considered peasant superstition. Black holes were mathematical curiosities that couldn't possibly exist, until they did. And now, we're in a new phase of that evolution. The idea that we might detect evidence of extraterrestrial technology, not through radio signals from distant stars, but through physical objects passing through our solar system. That's no longer science fiction. It's a legitimate scientific hypothesis that deserves investigation. The term for this is technosignatures, evidence of technology created by non-human intelligence. SETI, the search for extraterrestrial intelligence, has been scanning the skies for radio signals for decades. That's one type of technosignature. But physical artifacts, probes, spacecraft, those would be technosignatures too. And if you're going to send a probe across interstellar distances, you're not going to make it obvious. You're going to make it robust, self-sufficient, and probably indistinguishable from natural objects to anyone who isn't looking closely. That's what makes 3I Atlas so unsettling. It looks almost natural. Almost. But there are these little details, these anomalies, that don't quite fit. The nickel alloy, the anti-tail-to-tail transition, the extreme CO2 dominance, the water production at impossible distances, the structural integrity over billions of years. Individually, maybe you can explain each one away, but together, they form a pattern, and patterns demand attention. Now, let's talk about what this object is actually doing as it moves through our solar system. Its trajectory is well mapped at this point. It came from the direction of the constellation Ursa Major, the Great Bear, traveling at about 58 kilometers per second relative to the local standard of rest. That's the average velocity of stars in our galactic neighborhood. Not particularly fast for an interstellar object. Oumuamua was faster. It entered the solar system from above the ecliptic plane. That's the flat disk where most planets orbit. Coming in at an angle like that is actually pretty common for interstellar visitors. They're not bound by our solar system's geometry. They approach from whatever direction their galactic orbit happened to carry them. As it got closer to the Sun, gravity bent its trajectory into the hyperbolic arc we're tracking now. It swung past Mars in early October, close enough for the high-rise camera to grab those images we still haven't seen. Then it continued inward toward perihelion. After October 29th, after it rounds the Sun, the trajectory will carry it back out of the inner solar system at a different angle. It'll cross the orbit of Mars again in late November, but much farther from the planet this time. Then it'll pass through the asteroid belt, cross Jupiter's orbital path sometime in early 2026, and eventually leave the solar system entirely. The exit trajectory will take it toward the constellation Lyra, different direction than it came from, because the sun's gravity altered its path. That's normal. What wouldn't be normal is if the trajectory changes in ways that can't be explained by gravitational interactions. And that's what scientists will be watching for after perihelion. Any deviation, any course correction, any acceleration that doesn't match the expected physics, that would be significant. Because if this thing is artificial, if it has any kind of propulsion system, then it might use the perihelion passage as cover to make adjustments. While it's behind the sun, while we can't observe it, it could fire engines, change velocity, alter course. And by the time we see it again in November, it could be on a completely different trajectory. We won't know if that happened until we get fresh observations. And even then, small changes might be hard to detect. But if there's a significant deviation, if 3I Atlas emerges from perihelion moving faster or slower than expected, or heading in a direction that doesn't match gravitational predictions, then we'll have our answer. Not proof, maybe, but strong evidence. The challenge is that space is complicated. There are a lot of factors that can influence an object's trajectory. Solar radiation pressure, outgassing forces, even the gravitational influence of planets millions of miles away can have subtle effects. Calculating the expected trajectory requires accounting for all of those variables. But that's what astronomers do. They model these systems. They run simulations. They predict where an object should be based on the known physics. And then they compare those predictions to observations. If the observations match the predictions, great. The object is behaving as expected. But if there are discrepancies, unexplained deviations, then you start asking why. With 3I Atlas, there's already been one unexplained deviation. Back in August, some researchers noted that the object's brightness changed in ways that weren't fully consistent with a simple rotation model. Comets often vary in brightness as they rotate, because different sides of the nucleus reflect different amounts of light. But 3I Atlas's brightness variations didn't follow the pattern you'd expect from a uniformly rotating irregular object. It could be that the nucleus has an unusual shape, or that the active regions are distributed asymmetrically, causing brightness spikes when jets are pointed toward Earth. Or it could be that the object isn't rotating uniformly. Maybe it's tumbling in a complex way. Or, and this is the uncomfortable possibility, it could be that the brightness variations are related to something other than rotation, like orientation changes, like active maneuvering. Again, we're in this frustrating space where every observation can be interpreted multiple ways. And without more data, without those high-rise images, without high-resolution spectroscopy from multiple angles, we can't definitively rule anything out. But here's what we can say. 3I Atlas is behaving differently from any comet we've studied in detail. And it's doing so in ways that are at least consistent with the artificial object hypothesis. That doesn't mean it is artificial. It means we can't exclude the possibility. And given the implications, that's enough to warrant serious attention. So what would it mean if 3I Atlas actually is some form of alien technology? First, it would confirm that we're not alone in the universe. That's the big one. The question that humanity has been asking for millennia would finally have an answer. There is other intelligent life out there. Or at least, there was. Because remember, this object is billions of years old. The civilization that built it, if it was built, might not exist anymore. Second, it would tell us that interstellar travel is possible. Not just theoretically possible, but actually achievable. Some civilization figured out how to send objects between stars, and did so on a scale where those objects are reaching us with measurable frequency. Third, It would raise massive questions about intent and capability. Why send probes to other star systems? What are they looking for? What are they designed to do? Are they autonomous, or are they reporting back somehow? And if they're reporting back, to where? To whom? And fourth, it would fundamentally change our approach to astronomy. Every asteroid, every comet, every interstellar visitor would need to be scrutinized not just as a natural object, but as a potential artifact. We'd need new protocols, new observational strategies, new ways of thinking about what we're seeing in the sky. The implications are staggering, which is why most scientists are hesitant to embrace the artificial object hypothesis without overwhelming evidence. The bar is high, and it should be. Extraordinary claims require extraordinary evidence, but the evidence is starting to accumulate. And with each new observation, each new anomaly, the question becomes harder to dismiss. Let's circle back to the tail for a moment, because the timing of its appearance is worth examining more closely. The anti-tail was first documented in early August, when 3I Atlas was still relatively far from the Sun, around 2.5 AU. At that distance, the object was already active, already outgassing, and the material was being expelled forward. Fast forward to September, and the Nordic Optical Telescope captures images showing a traditional tail streaming behind the object. The transition happened somewhere in that window, probably late August or early September. That's roughly when 3I Atlas was passing through the 2 AU mark, twice the Earth-Sun distance. The solar radiation at that point is about 4 times less intense than what Earth receives, but still significant enough to drive sublimation of volatile materials like CO2. The question is, why did the anti-tail stop and the regular tail start at that specific distance? If it's purely natural processes, then maybe there's a threshold. Maybe at greater distances, the rotation and outgassing dynamics favor forward-directed jets. And as the object gets closer and solar radiation increases, those dynamics shift and the tail starts forming in the traditional manner. Possible, but it requires a pretty specific set of conditions to work out that way. If it's artificial, then maybe 2 AU was the target distance for completing the braking maneuver. Maybe the propulsion system was designed to fire until the object reached a certain distance from the Sun, and then shut down. At that point, natural outgassing takes over, and the tail forms normally. Also possible. And honestly, from an engineering standpoint, it makes sense. If you're trying to slow down an interstellar object as it enters a solar system, you'd want to complete the maneuver before you get too close to the star, where thermal stresses and radiation could interfere with your systems. 2. AU seems like a reasonable distance to aim for. Far enough to avoid the worst of the solar environment. Close enough that you've captured into a trajectory that will take you through the inner system for observation purposes. But this is speculation. Informed speculation based on what we know about orbital mechanics and spacecraft design, but speculation nonetheless. What's not speculation is that the transition happened. It's documented in multiple independent observations. The anti-tail was there, and now it's not. The regular tail is there, and it's growing. Something changed. The object's behavior shifted at a specific point in its approach to the Sun. And that shift is either a coincidence, an artifact of comet physics we don't fully understand, or evidence of deliberate action. Scientists are going to be analyzing this transition for years. They'll model every possible natural mechanism, test every hypothesis, run simulations, compare 3I Atlas to other comets, and eventually we'll get closer to an answer. But for now, we're left with uncertainty. And uncertainty, in a case like this, is almost more fascinating than a definitive answer, because it means the door is still open. The possibility is still live. Let me give you another detail that hasn't gotten as much attention, but is equally strange. The cyanide. Yes, cyanide is found in comets. It's a common byproduct of organic chemistry in space. But the amount of cyanide 3I Atlas is producing is unusually high. Spectroscopic observations show strong emission lines corresponding to CN, the cyanide radical. In typical comets, cyanide is present but not dominant. You see it, but it's not a major component of the coma. With 3I Atlas, it's prominent, which suggests either that the comet's interior is unusually rich in cyanide-bearing compounds, or that something about the outgassing process is preferentially releasing cyanide. Why does this matter? Because cyanide chemistry is complex. It's involved in the formation of amino acids, the building blocks of proteins. It's part of the prebiotic chemistry that might have led to life on Earth. Finding high concentrations of cyanide in an interstellar object is scientifically interesting from an astrobiology perspective, but it's also interesting from another angle. Cyanide compounds can be used as propellants. In chemical propulsion systems, you need materials that release energy when they decompose or react. Cyanide-based compounds fit that bill. They're not the most efficient propellants we use on Earth, but they're effective, and they're composed of elements that are abundant in space. Could 3I Atlas be using cyanide chemistry as part of a propulsion system? Could that explain the high CN concentrations? It's a stretch. It really is. But it's the kind of detail that, when combined with everything else, makes you wonder. And that's the position we're in with this object. Wondering, questioning, trying to fit together pieces of a puzzle that might not even be complete yet. October 29th is going to be a critical day. Telescopes around the world will be locked onto 3I Atlas, recording every photon of light reflected or emitted from the object. Spectrometers will break down that light into its component wavelengths, revealing which molecules are present and in what quantities. Photometric instruments will measure brightness changes down to tiny fractions of a percent, and then the object will disappear behind the sun, and we'll wait. The waiting is going to be difficult, not just for scientists, but for anyone paying attention to this story, because we'll know that something extraordinary is happening just 100 million miles away, and we won't be able to see it. It's like watching a thriller and having the screen go black right at the climax. You're left in suspense, forced to imagine what's happening, unable to do anything but wait for the next scene. And when 3I Atlas reappears in early November, that's when the real analysis begins. That's when we'll see if it survived perihelion intact, if it fragmented, if it changed. That's when we'll measure its new trajectory and compare it to the predictions. That's when we'll start getting answers. Or, more likely, that's when we'll get more questions. Because objects like this, they don't tend to provide clean, simple answers. They raise complexity. They challenge assumptions. They force us to expand our understanding. And maybe that's the point. Maybe the universe is trying to tell us that we don't know as much as we think we do. That there's still mystery out there, still wonder, still things that defy easy explanation. 3I Atlas, whether it's a comet or something else, is a reminder of that. A reminder that we're still explorers, still discoverers, still students of a cosmos that's far stranger than we ever imagined. Think about the timing of all this. We're living in a unique moment in human history. For the first time, we have the technology to detect and study interstellar visitors in detail. 50 years ago, 3I Atlas would have passed through the solar system completely unnoticed. 100 years ago, we didn't even know other galaxies existed, let alone that objects could travel between star systems. But now, we have automated survey telescopes scanning the sky every night. We have space-based observatories with capabilities that would have seemed like science fiction a generation ago. We have international networks coordinating observations across continents. We have the tools to see these visitors, to track them, to analyze them. And what we're finding is that the universe is far more dynamic, far more populated with wandering objects than we ever suspected. The solar system isn't a closed box. It's permeable. Things come through all the time. And occasionally, one of those things is strange enough to make us question everything. There's another aspect to this that's worth considering: the public reaction. Or rather, the lack of it. Right now, as I'm speaking, a potentially alien spacecraft is racing toward the sun, and most people have no idea. It's not leading the news. It's not dominating social media. It's a niche story, covered by science outlets and space enthusiasts, but largely invisible to the mainstream. Why? Part of it is fatigue. We've been teased with the possibility of alien life for so long that people have become desensitized. Every few months, there's a new headline about possible biosignatures on Mars, or mysterious signals from space, or anomalous objects. And every time, the story fizzles. The biosignature turns out to be geology. The signal is interference. The anomaly is explained. People have learned not to get excited until there's definitive proof. And with 3i Atlas, we don't have that. We have anomalies, yes. We have questions, absolutely. But we don't have proof. And maybe that's appropriate. Maybe we shouldn't be jumping to conclusions. Maybe the scientific approach, the careful analysis, the insistence on extraordinary evidence is exactly the right way to handle this. But there's a part of me that wonders if we're being too cautious, if we're so afraid of being wrong, so afraid of looking foolish, that we're not allowing ourselves to seriously consider the possibility that we're witnessing something historic. Because here's the reality. If 3i Atlas is artificial, we're living through first contact. Not the Hollywood version, not aliens landing on the White House lawn, but the real version, an artifact from another civilization, passing through our neighborhood, potentially observing us, and we're observing it right back. First contact might not be a conversation. It might be this. Two intelligent species, separated by billions of years and trillions of miles, briefly sharing the same cubic light year of space. One of us leaving behind technology that survives long enough to be detected by the other. It's not dramatic. It's not explosive. It's quiet, subtle, easily missed if you're not paying attention. And that might be the most profound version of contact we could hope for, because it doesn't require the aliens to still exist. It doesn't require them to be interested in us specifically. It just requires that they, at some point in the deep past, figured out how to send objects between stars. And we, now, have figured out how to see those objects when they pass through. That's a kind of dialogue. A dialogue across time and space, mediated by physics and technology. And if that's what's happening here, if 3i Atlas really is an artifact, then the fact that most people don't know or don't care is both tragic and oddly fitting. Because this is how the universe works. It doesn't announce itself. It doesn't make things easy. You have to look closely. You have to pay attention. You have to be willing to ask uncomfortable questions. Now, let's bring this back to the immediate future. What should we be watching for in the coming weeks? First, the perihelion passage on October 29th. Any unusual activity, any unexpected changes in brightness or tail structure, those would be significant. If 3i Atlas suddenly brightens by orders of magnitude, that could indicate a massive outburst or fragmentation event. If it dims unexpectedly, that could suggest that the active regions have shut down or that the object has reoriented. Second, the high-rise images, if and when they're released. Those images could provide visual confirmation of the object's structure. Is it irregular and lumpy like a natural comet? Or is there something about the shape that doesn't fit natural formation? Linear features? Symmetry? Structures that look engineered? Third, the November reemergence. When 3i Atlas becomes visible again after perihelion, the first observations will be critical. Measure the brightness, the tail length, the spectroscopic signature. Compare everything to the pre-perihelion data. Look for changes. Look for anomalies. And fourth, the trajectory. This is the big one. After perihelion, astronomers will calculate the object's new trajectory with high precision. They'll compare it to the predictions based on gravitational modeling. If there are discrepancies, if the object is moving faster or slower than expected, if it's heading in a direction that doesn't match the predictions, that would be evidence of propulsion. Evidence of maneuvering. That's what we're waiting for. 4 key data points that could shift this story from interesting comet with unusual properties to potentially artificial object requiring immediate further investigation. And if the trajectory shows evidence of propulsion, then what? Then the entire scientific community mobilizes. Every major telescope gets redirected. Space agencies start planning missions. Governments get involved. Because at that point, we're not just observing a curiosity. We're observing evidence of extraterrestrial technology. And the questions multiply. Where is it going? What is it doing? Can we communicate with it? Should we try? What protocols do we have for this kind of situation? The answer to that last one, by the way, is not many. There are some frameworks, some guidelines developed by SETI researchers and space policy experts. But they're not comprehensive. They're not legally binding. And they certainly weren't designed for a scenario like this, where the evidence is ambiguous and the object is already leaving. We'd be making it up as we go, which is both terrifying and exciting. But let's not get ahead of ourselves. Right now, the most likely explanation is still that 3I Atlas is a natural object with some unusual but ultimately explainable properties. Occam's razor still applies, even if the razor is getting a bit dull from all the anomalies we're trying to shave off. The scientific consensus, if you can call it that, is cautious optimism. Optimism that we're studying something truly unique and scientifically valuable. Caution about jumping to extraordinary conclusions without extraordinary proof. Avi Loeb is an outlier in this regard. He's willing to publicly entertain the artificial object hypothesis in a way that many of his colleagues aren't. And he's been criticized for it, accused of seeking publicity, of being too quick to invoke aliens, of damaging his scientific credibility. But here's the thing. Someone has to be willing to ask the uncomfortable questions. Someone has to be willing to look at the data and say, this doesn't fit our models, and maybe that's because our models are incomplete. Someone has to push the boundaries, and if Loeb is wrong, if 3I Atlas turns out to be entirely natural, well, we'll have learned something anyway. We'll have better data, better models, better understanding of cometary behavior. Science progresses through questions, not just answers. But if he's right, if there's even a kernel of truth to the artificial object hypothesis, then Avi Loeb will go down in history as the person who first seriously proposed that we detected alien technology, and the rest of us will be scrambling to catch up. There's one more thing I want to touch on before we wrap this up. The emotional dimension. How should we feel about 3I Atlas? If it's a comet, we should feel wonder. This is a 7 billion-year-old relic from the early universe, carrying chemical signatures from a star system that might not even exist anymore. It's a message in a bottle from the distant past, delivered to our doorstep by the currents of the galaxy. That's extraordinary. If it's artificial, then wonder isn't enough. We'd need a new emotion entirely. A mix of awe, humility, excitement, and maybe a little fear. Because it would mean we're not alone. It would mean that intelligence arises elsewhere in the universe, and that it can create things that endure for billions of years. It would mean that somewhere out there, or when out there, another species looked up at the stars and decided to reach out. To send something. To make their presence known, even if only as a fading echo in the vast darkness. And we'd be hearing that echo now, across billions of years and light years of space. We'd be connected to them, Not through conversation, not through understanding, but through the simple fact that we both exist, that we both wondered, that we both tried. That's what Three-Eye Atlas might represent. And whether it's a comet or a craft, that's worth paying attention to. So here's where we are. In 4 days, Three-Eye Atlas reaches perihelion and disappears behind the sun. For 2 weeks, we wait. And then, in early November, it reappears. We measure, we analyze, we compare, and we find out if we're living through one of the most significant moments in human history, or if we're just observing another fascinating chapter in the story of comets. Either way, we'll know soon enough. Until then, somewhere between Mars and the Sun, a Manhattan-sized object from another star system is putting on a show, growing a tail, racing toward its closest approach to our star, potentially maneuvering, potentially just being a comet. The telescopes are watching, the data is accumulating, the questions are multiplying, and the universe, as always, keeps its secrets just a little while longer.